Hi, welcome to my channel, JaberTime. Here's another example about the kernel and the range of T transformation. The transformation is going from R to the third to R to the third, and the matrix of transformation A is a 3 by 3. Find the kernel and the range. There's more into it, so let's get started. That's the problem again. We're going to find the kernel, the range, and we're going to give a geometrical description of each. Also find the dimension of the kernel, the dimension of the range, and verify the General Rank-Nullity Theorem. Let me remind you about row operations. Row operations. You could permute the ith and the jth row of A. You could multiply every element of the ith row of A by a non-constant scalar k, just like systems of equations. You could add the elements of the jth row, that's aijk, of A, the scalar k times the corresponding elements of the ith row of A. So you could multiply the ith row with a k, go to the jth row and add them to the jth row and keep them there. Of course, this is kind of dry. We're going to see it practically with our example. Something interesting that I would like to mention: if you're going from R to the n to R to the m, the transformation is AX with the matrix of transformation A. A has the size and has to have the size m by n. M by n. Why? So if it's m by n and you multiply by elements x, or vectors, I said elements, vectors in R to the n, the size of any vector in R to the n will be n by 1. So R to the third would be like 5, 7, 2. So it's a 3 by 1 as a column, as a vector. So notice that n matches, and the result will be m by 1. So the output of this product will be m by 1, which actually belongs to the outputs w, in this case R to the m. Just something to keep in mind. What is the kernel? The kernel is the set of vectors in our set V, in this case R to the n, such that their images takes you to the 0 in R to the m. That's the definition of the kernel. Differently, instead of writing tx equals 0 as outputs, we could rewrite that as ax. And usually we refer to that as a homogeneous linear system. The kernel of T is a solution set to the homogeneous linear system because it's kind of like a system of equations, but after the equal sign to the right side, it's all zeros. So that's the kernel. That is, the kernel is called the null space of A, or a subspace of R to the n. So we're looking for the vectors right here. We call it null space because of the 0, and they belong, it's the set of vectors in R to the n. A subspace of R to the n. What is the range? The range are the vectors here that they are images to this kind of transformation. Could be onto, could be all of it, and it doesn't have to be. So the range will be t of x, that's my outputs, such that we take those x's from V or R to the n. So the name of the kernel is the null space. The name of the range is the call space of the matrix A. It's a subspace of r to the m, which could be all of it, but it doesn't have to be. Also, to help you with the kernel, let's go back to some ideas or some thoughts that we need. Here's the definition. The dimension of a finite dimensional vector space V, written dim or dim dimension V with brackets, is the number of vectors in any basis. That's when we look at the basis of V. By definition, if V is the trivial vector space, V equals the vector space 0 or the vector 0 only, then we define its dimension to be 0. I know you might say like it has a vector, so why we should maybe think about it as size of 1, but no, by definition we say that the dimension is 0. So everything should work out and add up in the General Rank Theorem and some other theorems. The General Rank-Nullity Theorem says if you're going from V to W under a transformation T, linear transformation, and V is finite dimensional, then the dimension of the kernel plus the dimension of the range will add up to the dimension of V itself. So here's our problem again. That's my V, that's my W, the matrix of transformation. We're going to talk about everything right here, and let's get started. To do it, it's simple matrix operations, keeping in mind that we need to write this in reduced row echelon form. Before we do that, Ax equals 0, we're thinking about kernel. That's going to be times x, which is x1, x2, x3, equals 0, 0, 0. In short, we call it augmented matrix. One more time, we're going to set it equal to 0. Q of x, that means A times x, equals 0. So if writing x and writing equal and writing zeros on the right side, we call it augmented matrix of the system. And that is augmented matrix of the system. This refers to A times x, you don't see the x right here, equals 0 on the right side. We need to reduce this. We have the 1 here handy, so we need to move on. This is a 0, which is fine. We need to change this 2 to 1. And the way to do it is we're going to multiply the first row by -2, go down to the third row, add it to it, and keep it in the third row. So in short, we call it A1, 3. Multiply the first row by -2, go to the third row, and add your results right there. That's my steps right here for this operation right there. So we're going to multiply the 1, the -1, the 0, and the 0. So once, twice, 3 times, 4 times. 1, 2, 3, 4. Here we go. First one, -2 times 1. Once you're done, we're going to add it to 2 and put the answer here. -2 times 1 plus 2. That's -2 plus 2, which is 0. So right here, we're going to write 0. Here we go. Second element, we're going to go -2 times -1. Let me write it down for you. And go down to the third row, add that to -1. So it's +2 and -1, which is 1. That goes right here. Third element, 0. Nothing's going to change when you multiply, but when you add to 1, it's going to stay 1. -2 times 0 plus 1, 0 plus 1, which is 1. We're going to write it right here. At the end, nothing is going to happen. It's all zeros. -2 times 0 plus 0, which is 0. We're going to write it here. Nothing changes, so we're going to write 0 down below right there. Okay, so far so good. Now we need to think about moving forward, and -1 has to be +1. Of course, I'm not going to multiply by -1 because that will fix this, but that's going to change this to a -1. We don't want that. So the way to do it is a little bit different. Here we go. We need to change this to 0. I mentioned 1, by the way. My mistake. We need to change it to 0. To change it to 0, we bring its opposite. I could see the opposite right here. And we're going to do the following. We're going to multiply this by 1 and go up here. 0 is good to have in our way, so it won't change the 1, and the rest will follow. Here's the first part. We're going to multiply row 2 by 1, go up to row 1 and put the results right there. 1 times 0 plus 1 and keep it there. 1 plus 0, 1 times 0 is 0, plus 1, that's a 1. So this is not going to change, as you could see. Now, 1 times 1 is 1. Add it to -1. That's my second part. 1 times 1 is 1. Add it to -1, which is 0. So that's a 0 right there. Moving forward, 1 times 2 is 2. Added to 0 will be 2. 1 times 2 plus 0. 1 times 2, which is 2, plus 0 is 2. That's going to go right here. Finally, 1 times 0, 0. Added to 0, nothing's going to happen. So it's going to stay 0. So far, so good. Now, I have 1 and I have 0. Moving forward in a diagonal way, that's a 1. That's good to have. We need to change this to 0. So if we change this to 0, we're going to have this pivot element 1 above it and below it zeros to have it reduced form. So let's do that on a different slide. Changing this 1 to 0, I need to bring its opposite. And that's the best number to look at to work on it. So I'm going to multiply this by -1 and go down and add it to 1 to force it to be 0. -1 times 1. Notice I skipped this one because that's a waste of time to multiply -1 times 0 and add it to 0. Nothing's going to happen. So -1 times 1 is -1 added to 1, which is 0. Next, -1 times 2, -2 added to 1, that's -1. Next, -1 times 0 added to 0 is not going to change anything. So that's my 0 down here, and that's my -1 down here. Next, moving forward in a diagonal way, I have these two 2's. I could bring the opposite, which is -2, and change them to 0. But instead of multiplying this by -1 and make it 1, then multiply by -2, I already have the negative sign, so I'm going to multiply by 2 and go up. So we need these 2's to be 0. We're going to multiply the third row by 2, because I already have the negative sign, and go up to the second row. We'll do the same thing, multiply the third row by 2, but now this time go up to the first row. That's like 2 steps in one. That's like 2 birds, 1 stone, if you like that. Let's move on. 2 times -1, -2, added to 2, 0. Notice I'm not mentioning the zeros right here. They're not going to do anything. They're not going to change anything, which is good. So that's going to change to 0, and both ways it's the same numbers. So I don't have to copy this again and again. All right, so far so good. We're almost done. We just need this to be +1. So we use the second method in row operations, which is multiply m. We're going to multiply the third row by -1 and keep it there. That's called m3 -1. That will change it to 1. Now I see the ones in a diagonal way. I see zeros everywhere else on that, on those columns. So what we have accomplished is we started with the augmented matrix with row operations. It came up just like that. It doesn't have to be always like ones and zeros. It could be like something else. It could be ones, 1 here, zeros here, and so on. But it doesn't have to be like always perfect like this, ones and zeros, like the identity matrix. But that's our example. So we call this one reduced row echelon form. And in math, we don't like to write everything. We like symbols. I don't know, maybe we're kind of lazy, but repeating over and over and over, we like to use symbols. The best symbol is X for the unknown. And here we go. In short, we call it RREF, reduced row echelon form. Now, what does this translate to? Translates to the following. Remember when I mentioned this column as an equal sign? Here we go. That's my equal sign. And those are my zeros on the right side. That's 1x1 plus 0x2 plus 0x3 equals 0. Second row reads 1x2. Third row reads 1x3. Reading this in a clean look, that's what it means. x1 equals 0, x2 equals 0, and x3 equals 0. When I say x3, I mean x as an index 3, not just x3 or the third x. It's a third element like ABC. Now, meaning that they are all zeros. They are all equal to 0, which is the origin. So, what does this mean? We have the kernel. It's just the 0 vector. Geometrically, this describes the origin in r to the third. And what did we say about the dimension? When you have a vector space that consists only of the 0 vector, we don't say 1, we say 0. So the dimension of the kernel is 0. Done with the kernel, let's jump into the range. The range is the call space. And I have my notes right here that shows we started here, we ended up here. But the range from the row echelon form of A, we're looking right here, we see that the call space is generated by the corresponding. We don't take these vectors, we take the corresponding vectors of A that corresponds to the column vectors of the row reduced echelon form or reduced row echelon form. What does this mean? You see the word corresponding. I'm using a different color because I want to emphasize that for the call space, we are looking at the ones. And now we go back to find the corresponding ones, which is these 3 vectors. That's the call space. Meaning the vectors are 1, 0, 2, -1, 1, -1, and 0, 2, 1, which give a basis for call space A, a subspace of r to the third. So what is the range? The range is actually the entire r to the third, because we have 3 independent vectors which builds or forms the basis for the range. The dimension of the range is the dimension of r to the third, which is 3. The bases, as I mentioned, are these 3 independent vectors in r to the third. Geometrically, this describes the whole r to the third. All right. Now we go back to the General Rank theorem, nullity theorem. The dimension of kernel plus the dimension of range equals the dimension of V, and this is my V, which is r to the third. We found the kernel to be the 0 vector only. We found the range of T to be those 3 vectors as bases. And we know that the dimension of r to the third is 3. So putting the numbers in, 0 plus 3 equals 3. Okay, we are done. But why not? Since I have my notes and you have now everything, you know the kernel, you don't know the range. Let's talk about something else. It takes like a minute. It doesn't hurt. Problem is done. But I want to add something to it. Why not? I'll call it bonus, as you could see. We know the problem. We know what's V. We know what's W. We answered everything they want. But knowing that the kernel is 0, it means something. Knowing that the range covers the entire W, it means something else. We've done everything, so let's reduce the talk and the time of recording and show you what do I mean. This means 1-to-1. Since the kernel is 0, that's called 1-to-1. The transformation is 1-to-1. Since the range covers the entire r to the third, meaning W, it's going to be onto. There is more into it. If T is 1-to-1, we have the dimension of V less than or equal to the dimension of W, which is true. V is r to the third and W is r to the third. T is onto, which means the dimension of V is greater than or equal to dimension of W, which is true. Dimension of r to the third is greater than or equal to the dimension of r to the third. Of course, the equal sign is valid, so we say yes, it's true. But in our case, that means 1-to-1 and that means onto, so we have it 1-to-1 and onto. And that is true. Dimension of r to the third, so I'm calling it V, equals the dimension of W, which is also r to the third. And that should do it. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.